Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about a very interesting technique which is called as collaborative filtering. We will be looking at two important algorithms in RStudio. One is called as user-based collaborative filtering and the second one is called as item-based collaborative filtering. Even before I proceed to demonstrate how to execute a collaborative filtering model in RStudio, may I request you to subscribe to my channel, also like and share my videos. In my last video, we spoke about similarity metrics and what exactly is recommendation engine. This is part 2 of the same series. Let's begin by asking a simple question as to what exactly is collaborative filtering and why do we need collaborative filtering. Collaborative filtering is becoming a very integral part of recommendation engine. I repeat, collaborative filtering is becoming a very integral part of recommendation engine. There's a typical problem in the e-commerce world. This problem is present in today's connected world of e-commerce space, where we observe long tail problem. What exactly do we mean by the long tail problem? In today's business world, there are tens of thousands of products. There could be millions and millions of books, or there could be many songs or movies. In a brick and mortar world where you had a shop, you had, let's say, merely 20 to 30 products. Someone buying an item, you could automatically recommend other items to this person because the choice of products is limited in a brick and mortar world. However, in today's day and age, wherein there are millions and millions of products, it becomes very difficult in an e-commerce space to make the optimal recommendation. This is where there is a bit of a challenge. If somebody likes a product, he buys a product or he clicks on an item, what else could we recommend? So this is the central question. This is the most important question that a recommendation engine answers. That is, if you were to buy a particular product, which other product can I recommend to you? We see this all the time in e-commerce space, wherein when we buy something in Amazon, Amazon will automatically recommend some products. Say, for example, movie tickets. They will send you a mail depending upon the movie choices that you've made earlier. Basically, a recommendation engine recommends new products based on your past buying behavior. I repeat, a recommendation engine recommends new products based on your past buying behavior. Now, as I mentioned, typically there are two types of recommendation engine. One is what is called as IBCF, and the second one is what is called as UBCF, user-based collaborative filtering, and the second one is item-based collaborative filtering. We'll talk more about IBCF as well as UBCF. Let's look at some of the codes that we have written. The first step here is to load the package in R, which is called as Recommender Lab. I repeat, this is a package which is called as Recommender Lab. I will go ahead and execute the library. This will activate the functions that are present in Recommender Lab. For this video, I will be using a data set which is called as Movie Lens dataset. If you have an account in Movie Lens, you can go ahead and give your ratings for different movies based on your past choices, based on the ratings that you have given to some of these movies. Movie Lens would make recommendations for the kind of taste that you have in movies. Let's quickly look at the data structure. So when you click on structure of Movie Lens in the console window, you can see R displays the structure of the data set. It says real rating metrics with 2 slots. There's a better way of displaying the data set. Let me pull out the slot names and convert this as a data frame. When we convert this data into a data frame, you can see here RStudio tells me that there are 99,392 observations and 3 variables in this data set. There are 3 variables. Which are these 3 variables? The first one is the user. This is the user ID. We are talking about the first person, and therefore the first 4 numbers are the same, which means we are talking about the first person. The items that he has earlier purchased are Toy Story, GoldenEye, 4 Rooms, Get Shorty. Look at the ratings that he has given. The ratings that he has given are 5, 3, 4, 3, 3, so on and so forth, which means that he has given the highest rating for the movie Toy Story. He has given a rating of 5. So this is the data set that we will be working on. There are many algorithms that are present in this particular package. Even before we explore some of these algorithms, let's just display the header of the row. You can see here, it's a better view here. You can see here the first person with ID number 1, user ID is 1. We have already seen this. He has purchased Toy Story. He has given a high rating of 5 to the movie Toy Story. If you look at GoldenEye, he has given it a neutral rating of 3. When you look at 4 Rooms, he has given a reasonably high rating of 4. When it comes to Get Shorty, it is 3. Copycat, the rating is 3. And when it comes to Shanghai Triad, the rating is 5. Looks like this person has liked 2 movies, namely Toy Story as well as Shanghai Triad. No wonder he has given an extremely high rating. Like this, we have 943 customers in this data set. We also have 1,664 records in this data set. Sorry, my apologies. We have 1,664 movies. So we have 943 records of customers and 1,664 movies in this data set. We would like to build a prediction model which generates the prediction about the preferred movies for each and every customer. Let's check out some of the important algorithms that are present. You can see here, recommender registry $get entries. This will give me the list of algorithms that Recommender Lab has. It prints a lot of information here. Let's just look at some of the important information and important algorithms that are present in Recommender Lab. Yes. Let's look at some of the important algorithms. The first important algorithm, you can see here, a recommender method. It says hybrid for real rating metrics. The description he says is hybrid recommender that aggregates several recommendation strategies using weighted averages. So the first method that you can go ahead and try would be hybrid real rating metrics. We will not be working on this particular algorithm. Then there's another interesting algorithm which is called as ALS, real rating metrics, alternating least squares. This is useful especially when you have what is called as explicit data rating, right? When the person or when the customer has given explicit rating, you can use ALS. ALS to a large extent is also able to solve the problem of a cold start. You have another algorithm. This again is designed for implicit rating. So you have one flavor of ALS algorithm. When you have explicit rating, you also have another flavor which is called as ALS, implicit real rating metrics. These are all some of the algorithms that are present in RStudio. I'd like to really draw your attention to what we will be working on in today's video, which is called as IBCF real rating metrics. So this is what is called as item-based collaborative filtering, which simply means that recommendations of products will be made based on the similarity of products, which simply means that we know that if you're a movie buff, there's a lot of similarity between Sylvester Stallone's movies and let's say Arnold Schwarzenegger's movies. So people who have been watching Sylvester Stallone's movies, you can go ahead and recommend Arnold Schwarzenegger's movies and vice versa. The same argument holds good even for, let's say, songs. If you're a big fan of Kishore Kumar and you've been watching a lot of songs of Kishore Kumar, you can perhaps recommend to this customer Mohammed Rafi's songs and vice versa. Or let's say the third example that comes to my mind is books. If you're very fond of murder mysteries, crime thrillers, and such things, and you have been reading a lot of Agatha Christie's books, perhaps you would like to also read Dan Brown's books. There are wonderful books of Dan Brown, let's say Inferno, or it could be Angels and Demons, so on and so forth. These are all these are all thrillers. They belong to the genre of thrillers and murder mysteries and such things. So you can cross-recommend one set of books to people who have read another set of books. So item-based collaborative filtering is a strategy that we can use, wherein the model makes a recommendation based on the similarity of products. Just as you have what is called as item-based collaborative filtering, you also have another interesting strategy which is called as user-based collaborative filtering. What is this user-based collaborative filtering? Just as in the case of item-based collaborative filtering, we looked at the similarity of products. In the case of user-based collaborative filtering, we will be looking at the similarity of users. Let's say there are two people, Ashok and John. Both of them have gone to the same school, they have gone to the same college. By and large, they have done a same degree, that is, they have passed out of BTech, let's say. Ashok has bought 2 products out of the total list of 5 products. And Matthew might have bought the 3 remaining products. Let's say Ashok has purchased A and B product, and Matthew has purchased C, D, and E. What can you do here? Whatever items Matthew has purchased, but Ashok has not purchased, you can go ahead and cross-recommend those items to Ashok. Similarly, you can cross-recommend those items which Ashok has purchased, but Matthew has not purchased, to Matthew. So this works based on the similarity of users. If 2 users are very, very similar, you can cross-recommend their products. On the other hand, let's say Ashok is very, very dissimilar to a person called as Johnson. So because their dissimilarity is so high, it's a commonsensical solution, that is, don't recommend Ashok's products to Johnson and vice versa. So this is how your UBCF or user-based collaborative filtering model works. Let's go ahead and build a collaborative filtering model. So we will be building a collaborative filtering model. Now, the first step here would be to create what is called as an evaluation scheme, right? This is what is called as an evaluation scheme, which we will be building. What exactly is this evaluation scheme? Let me tell you. This is specific to recommendation engine in RStudio, because the person who has created this package has written the package in this particular format. Let's build an evaluation scheme. What this does is it simply splits the data into 3 parts. In line number 20, you can see here, we will be building a evaluation scheme. We are taking the movie lens as the input data set, and this would split the data. As you can see here, the value that we are providing for train is 0.9, or 90% of the records will be gone, will be pushed into the training data set. The remaining 10% of the data will be further broken down into test known and test unknown. So the value that method takes is split. You can also go ahead and experiment with cross-validation. So splits the data into 3 parts. One is training data set, second is test known, and the third one is test unknown. This is very strange, and sometimes people find this very weird. If you have built a typical machine learning model, what we do is we merely split the data into training and testing. Here it is slightly different because the person who has created the package has given this format. This is because the data structure here will be slightly different. Also, you see what is called as given equals 12. This is part of the internal testing that evaluation scheme does when it builds the model. So this is internal testing during the model building process, where it randomly picks up 12 ratings. and it compares the actual with the predicted. So this is part of internal testing. This has got nothing to do with the external testing that we do, wherein we build the model on training and predict it for the test. You can give any number here, given equals 12. You can also experiment with 5 or 6. It does not matter. So this is part of internal testing. This is what is called as model hyperparameter. It takes internally 12 records and checks out the prediction during the model building itself. So let me go ahead and execute this. All that we're doing here is to create a evaluation scheme by splitting the data and specifying some of the other parameters. Now that you have built the evaluation scheme, the next thing would be to display the contents of the evaluation scheme. You can see here, we have successfully built the evaluation scheme with 12 items. The method that we have used is split. This is the method that we have used. The data set, if you look at the sample size, it is 943 for 1664 rating metrics. Let's proceed to now extract the training data set. In line number 25, what we can do is you can use the get data command from the evaluation scheme and create your training data set. This training data set will be dumped in training object. This is a typical strategy while building any machine learning model. That is, we build the model on training and we generate the predictions. The predictions are scored. The predictions are obtained on the test data set. The test data set will be used to compare the actual with the predicted. So I have created my training data set successfully. The next step after creating the training data set would be to look at the training data set. So in line number 26, you can see here, I'm just typing TRG. So it says in the training data set, 848 records are present. Remember, in the original data set, which consists of the entire data, we have 943 records or customers. In the training data set, 848 records have been allotted. Next step, let's now pull out the test data. So there are two parts here. One is what is called as test known. So in line number 28, I will be typing this particular code, test known. Here, we are pulling out the test known. What is this test known? Test known will consist of the predictor variables, but not the dependent variable. Remember, this will not have the dependent variable. This will just have the predictor variable. Just as we have pulled out the test known, you can go ahead and examine the sample size for test known here. You can see here 95 by 1664. So this is the dimension of this particular object. Next thing that we would like to do is pull out test unknown. So in line number 30, let me just push it to the next line. You can see here, using the get data command, we will be extracting the test unknown. What is the sample size for test unknown? Let's look at the dimensions here. This again will be 95 by 1664. So we have created three objects: training, test unknown, and test known. The next step is where we will be building our first recommender model. We will be building two models. The first model will be a UBCF model, or user-based recommender model with the training data. So in line number 34, I'm just giving a comment here saying that we will be building a UBCF recommender model. This model is built on the training data. Let's now run the code here. You can see here a recommender. This is the function that we will be using. We will pass the input object here, which is the training data set. So this model is built on the training data set, and the argument that we are giving here, the value is basically UBCF. This is the value for user-based collaborative filtering. If you want to build a item-based collaborative filtering, the value will be IBCF. Remember, as I mentioned earlier, UBCF gives you the recommendations. My apologies. UBCF model would give you the recommendations based on the similarity of the users. Now that we have built the model on the training data set, what is the next step? You can clearly see here, you've stored the output of the UBCF model in what is called as a recommender underscore. In the next step, what we will be doing is we will be generating the predictions. You can see here in line number 34, we have built the model, and in line number 37, we will be creating the predictions. Remember, we will be using the test known values to generate the predictions. Once we use the test known to generate the predictions, we will be saving it as an object which is called as pred underscore UB. The type here that we are specifying is ratings. As a next step, we can go ahead and examine the predictions that our model has created. Pred underscore UB, this is the object name. Let me go ahead and execute this. You can see here 95 by 1664. This is just giving you the dimensions of the predictions that we have been able to create. Now, let us evaluate the model accuracy for the unknown set of test users. We have just now used test known, but we have not used test unknown. In line number 41, we will try to evaluate the model accuracy for the unknown set of test users. You can see here, calculate the prediction accuracy. How will you be calculating the prediction accuracy? The accuracy is calculated by simply comparing the predictions that you have made based on the test known with that of the test unknown. So we are comparing our predictions with the results that are present in the test unknown. If we go ahead and execute this particular object, let's look at the results that we are obtaining now. We have saved this as an object accuracy underscore UB. You can see here, these are the scores that we have obtained for the overall performance of the model. The first and the most widely used metric is what is called as Ramsey metric. It is popularly called as Ramsey or root mean square error. This is the most commonly used measure for evaluating the quality of prediction. Typically, if the Ramsey value is close to 0, you can go ahead and say that the model is good. There is no ideal value of Ramsey within which your model should lie, but lower the value of Ramsey, better the quality of prediction. Some people suggest that if the Ramsey value is between 0.2 and 0.5, the model is good. There are circumstances wherein the Ramsey value can be greater than 1. As you can see here, the Ramsey value in our case is 1.19. If the Ramsey value is greater than 1.19, it is typically an indication that the model did not identify the optimal solution. So that is one indication if the Ramsey value is greater than 1. You have other model diagnostic metric like MSE or mean square error, which is 1.41, mean absolute error, which is 0.94. For a good model, we want each of these measures to be closer to 0. What we have done just now is to look at the model prediction and create the accuracy measure. Let's now proceed to look at the results of our model. Here we can compare the results of our model. You can see here line number 45. In line number 45, we will just be comparing the results. We'll take a small data set. In fact, this is a sample of the data set for only a few records to understand this clearly. Along the columns, you have some of the names like Toy Story, GoldenEye, 4 Rooms, Get Shorty, and Copycat. This is the actual data that is present in test_unknown. Now, for the same set of records, let us generate the predictions in line number 47. You can see here, the values in the decimals are the predictions. So this is the prediction of the rating that our model has created. You're able to see two tables. This portion is the actual. This is the actual data. What you're seeing below in the second half is nothing but the predicted data. For the 6th person, the actual rating for Toy Story is 4. Our model has predicted the rating to be 3.6, which is not bad, very close to the value of 4. Let's look at the second case of GoldenEye. It says NA, we can ignore this. Let's look at the 18th person. The actual value is 5. The model has predicted this to be 4.14. Some difference, but not a big difference. For the 20th person, the actual value of rating that he has given for Toy Story is 3. And for the 20th person, the model has predicted the value as 3.64. 23rd value is 5. And here, the 23rd value is 4.30. Not bad. It looks like the model prediction is very close to the actual. So this is just giving you a glimpse of the performance of the model on a small set of 8 records and 5 movies. So when we are typing 1 up to 8, it simply means that we are looking at the first 8 records and the first 5 movies. This is only for us to understand the performance of the model. Now that we have built a UBCF model, so this is the end of a UBCF model. So far, what we have done is to build a UBCF model. Now, a UBCF model has many advantages. It also comes in with its own set of disadvantages. What are the 4 main drawbacks or disadvantages of a UBCF model or a user-based collaborative filtering? Thus far, we have built the model. We have looked at the model diagnostics in terms of Ramsey, mean absolute error, and mean square error. In terms of the drawback, the first major drawback is that a UBCF model suffers from user cold start. When we do not have much information about a new user for computing similarity, UBCF model fails. Remember, when we say UBCF, user-based collaborative filtering, it needs to have information about the user to compute the similarity. By definition, if a person is a new customer, we will not know about his past purchases, we will not know about his past rating, and therefore UBCF will not be able to compute the similarity. So this is the major drawback for a new customer, that is user cold start. UBCF fails. Let's proceed to look at the second problem, which is of data sparsity. Every user may not have rated every movie. That is, users may have rated only few films. That is, in the database, if you have 1,000 movies, I may have watched only 30 movies. So I can give a rating for only these 30 movies. What happens to the balance? 1,000 minus 30 movies, which is 970 movies, they will be unrated. So effectively, what you will have is 970 blank records or missing cases. So 970 blank cases for one record. If you have 1,000 such customers, you can imagine you'll have huge data sparsity issue. The third problem is scalability. When you have millions of ratings and thousands of customers, computation of the similarity for each customer with the rest of the customer becomes very, very difficult. And therefore, there are computational challenges while we build a UBCF model. The last problem here is that of item cold start. Now, what is this item cold start? For a new item, not enough ratings may be available. Let's say Apple has launched a new product. Not many people have seen this particular product. And since very few people have seen this particular product, very few ratings will be there. Since you do not have too much of ratings and such things, it becomes very, very difficult to cross-recommend this new product to a customer. So these are the four major hurdles that we see in a UBCF model: user cold start, sparsity problem, scalability issue, and item cold start. This is where we can go ahead and experiment with what is called as IBCF model. IBCF stands for item-based collaborative filtering. Let us go ahead and quickly build an item-based collaborative filtering. Which is very similar, just that we have to specify a different value to what we specified in the UBCF. Let me come to RStudio. We'll be repeating the process with a IBCF model. The command will be the same. You can see here, the command is recommender. We'll be building the model of the training data set. Here, I've changed the value to IBCF. If I scroll up, we have done something similar here. For UBCF, again, we have run the model on training, except for the fact that the value here is UBCF. So this is the only change that we will be making, that is in the value. Let me go ahead and execute this particular model. I think it's better to remove this. Next, let us go ahead and generate the predictions based on the IBCF model. Predict, here you can see the first value is recommend underscore IB. Based on test known, type would be ratings. So this will generate the predictions. If you want to inspect the predictions that have been generated, you can see here, it does not give you the values, but it just gives you the dimensions as 95 into 1664. Let us quickly calculate the predictions. How are we calculating the predictions? We have obtained the predictions based on test known. We have saved it as an object predict underscore IB. Now we'll be using a function which is called as calculate the prediction accuracy. We'll be comparing the model generated predictions with that of test unknown. We'll be saving the results in accuracy underscore IB. Let's use the rbind function and execute the accuracy metric. You can see here, as before, we have the model diagnostics, which is basically the Ramsey measure, root mean square error. We have the mean square error, and finally, we have the mean absolute error. There are two models. In the first stage, we went on to build a UBCF, and these are the results of the model that we are building now, which is IBCF. Clearly, when you look at the Ramsey measure, IBCF model is better than the UBCF model. Why do I say this? UBCF has a higher Ramsey value. However, when you look at IBCF, it has a lower Ramsey value. The same argument can be made for mean square error as well, because mean square error is lower in the case of IBCF. Mean absolute error of 0.66 is lower as compared to 0.94. So each of these model diagnostic measures, may it be Ramsey, may it be mean square error or mean absolute error, it is lower for item-based collaborative filtering as compared to user-based collaborative filtering, indicating that IBCF model outperforms UBCF model. We are not saying that this is a very, very good model. We might have to experiment, but out of the 2 iterations that we have done, IBCF model performs slightly better than the UBCF model. At this stage, I'd like to draw your attention to 2 important points. There are 2 major advantages of building an IBCF model. First one is that there is no user cold start problem here. In the case of UBCF, we found user cold start. In the case of IBCF, there is no user cold start issue here. The second important point here is that the similarity between items is more stable as compared to the similarity between users. So IBCF and the results of IBCF are more stable as compared to user-based collaborative filtering. Why do we say this? When you are looking at the similarity between users, when they give the rating, are influenced by the mood that they are in. If a person is in a good mood, you can expect him to give good rating. On the other hand, if the person is in a bad mood, for the same set of movies or for the same set of products, he might give you poor rating. When you go on to take this rating and then compute the similarity, it is slightly unstable. And therefore, we say that item-based collaborative filtering is more stable and more reliable as compared to user-based collaborative filtering. Let's look at the accuracy measures once again. We've already seen the accuracy measures. Now, let's just get a glimpse of the performance of the model. We will be generating the top recommendations. In line number 57, what we can do is we can get the top recommendation. We are making a prediction here and saving it as an object which is called as predict_top. So this will give you the top 10 movies that a person would buy. You see here in line number 61, what we are doing is we are generating the movies which are predicted as a list. For the first person, let's look at the top 10 movies which he is likely to buy. The first movie would be Pillow Book. Then we have Super Cop, Grand Day Out. Further, you also have Day the Earth Stood Still, Replacement Killers. These are the 5 movies that you can recommend. Apart from this, we also have other movies like So I Married an Axe Murderer. Then we have Close Shave, Jackie Chan's First Strike, and you have the next movie. So these are the top 10 predictions that we have been able to make for the first user. You can go ahead and look at the predictions for other users as well. So as you can see here, I have come to the end of today's video. In today's video, we have seen what exactly is a recommendation engine, what is collaborative filtering, how do we build 2 different types of collaborative filtering, user-based collaborative filtering, as well as item-based collaborative filtering. Based on these 2 models, we were able to compare the accuracy, and we found that UBCF model does not perform as well as a IBCF model. With this, I will end today's video. I request you to subscribe to my channel, also like and share my videos. Thank you very much for watching this particular video. Have a great day ahead.